Should be live now.
Here. Not sure if it's just our time zone, but I still have nothing, so it's probably going to take a second. Oh, there we go. Perfect.
Oh, yo.
Yo, yo, yo.
Yeah, you either need 10 million views on like videos, or you can do 4,000 watch hours.
That's it. I'll watch the whole stream if you want.
Yeah, I mean, you can just leave it, honestly, just leave it idle.
No, once you get monetized, dog.
Yeah, you don't, I mean, the best thing you can do is like type in chat like every like few minutes. Like,
Okay, I gotta change accounts then, just give me a sec.
Yeah, you're good.
Is it...
Did you like it already?
Yeah, I already did.
Okay, nice. Yeah, look at all my accounts. I'm loading up.
Damn, type shit.
Oh shit, better not say that on stream.
Yeah. Yeah.
Alright, let me call on Discord through my PC. I'll call you right back.
So.
This customer didn't trust anyone working on his driveway. When we pulled up, he came outside before we even unloaded the equipment. If you got him. This customer.
Yo, alright, 1 second. What?
Probably you started YouTube account and actually started pissing off.
Do you need to like verify something or? Yeah, I don't know if I can pull up the actual textbook on the stream. Yeah, yeah. I'm trying to find the.
Subscribers? That's
What?
that.
12,000 what? Yo. Because all like the people you sub to. Is that you? You're. Let's see here. Let's see if I can find the actual. Probably not. Oh, great. Oh, actually? Let's go. So what's four? What's 5 divided by 4,000? That's what 200. That's what 400. Oh no, that's 200. Wait, no, that's it's 200. It's two. Wait, no, it's 600. Yo, 4,000. Oh, it's 500. Wait. I'm so lost. Divided by 5. Actually, oh my gosh. So I need to stream. Oh, actually, Let's go. Now divided by 4,000 divided by 6. Okay, I might just have to read and then. Oh, you know what I could do? I have an idea. Oh my gosh, this book is $120 that I have. Holy. Oh no, I get it free. Okay, I guess I have an idea. I'm gonna do like text to speech or speech to text, and then like when I talk, it might pop up. Where is that? Right? What? Okay, what? Uh, oh my gosh. I don't need. Okay, I'm trying a new website. It cannot be this hard. I have an idea. For what? Oh, that's weird. Spamming the emojis. Yeah. Yeah, go ahead. I can spam it too. Yeah, no, I'm faster. I'm stronger. Just casually messaging on all my devices. Yeah. What? It's kind of chopped. I shouldn't have gave up on it. Okay, I just need to find a free non-AI. Oh my gosh. Why is it this hard? There's no way it's this hard to find a. There's no way it's this. What is it called? Speech what? I heard of that. No, it's AI voice. I mean, I don't care. I'm trying to basically me talk and then it puts it on words so you can, so it's like kind of on the screen. It's literally speech to text. That's literally all I need. I have an idea. I'm gonna go to Chrome.
Voice typer. You gotta install it though. Penis.
Yo.
Penis is showing up. Holy fuck. Oh, I see.
Hello. 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 It works. Okay, I found one. It's just, I don't know. It's just called. It's called speechnotes.co. Okay, let's get it. Okay, I'm gonna start. I gotta delete all this though, and I can't talk. Okay, we're on chapter 19 here. Oh no, chapter 16, not 19. I'm looking kind of. What? Your. Mine does. Oh, actually, that's funny. Okay, yeah, just make sure to text like every so often. I'm gonna lower your voice just so, or if you can talk, but I'm just every like page I'm gonna text. Anytime you hear me like stop. Do you want to mute me on here, or you just want to keep me unmuted? Can you hear me on stream? Okay, yeah, that's fine. I'm just gonna put you down on volume. I can still hear you though. Yeah. Okay, ready? Let's get it started. Okay, we're starting chapter 16, graphs and slopes. Learning how to take the derivatives and functions is absolutely crucial, requiring a lot of practice. We want to understand just what we're doing. One of the book's best way to understand derivatives, which are functions you'll recall, is to look at their graphs. By looking at this, we can actually see features and functions that are otherwise terribly abstract. This kind of visualization is important for mathematics in general, not just for calculus. Indeed, it's one of the main benefits of Kirstein's coordinates. In this chapter, we will take our time making sure that we truly understand the basic characteristics of derivatives by visualizing them on a graph. 16.1 Graphs. We've already seen, though quite a bit earlier in the course, that analytic geometry was one of the most fruitful ideas that any human had. Analytic geometry might be simply called algebraic geometry, since analytic meant roughly algebraic around Socrates' time, mid 1600s. Analytic geometry combines algebra and geometry, that is, numbers with shapes. After this marriage, mathematics began to advance at a lightning pace, resulting almost immediately in calculus. I took my headphones off, by the way. So far, by looking at formulas, we've focused mostly on the number realm, largely ignoring the world of shapes we've encountered, functions and their number. through formulas like these. dt equals negative 16t squared minus 35t plus 4. AR equals pi r squared. dy over dx equals lim to the alpha x of d, which is alpha y over alpha x. Such formulas are extremely effective ways to talk about numbers. Again, these formulas are really just sentences about numbers that could be written in ordinary English if you wanted to. But if we wrote them out in English, they would be long, cumbersome, and nearly impossible to understand. Putting them into symbols is much more efficient once we learn what the symbols mean. In any case, these sentences are about their subject, is numbers and their relations to numbers. They can also be about physical properties such as distance and time, but that takes an extra step. We have to go further and associate the numbers to these physical properties. Up to this point, we've been learning calculus by talking about numbers. We've been learning calculus by a way of the number realm. But in order to fully understand calculus, we need to also see the differentiation meanings in the world of shapes. We need to study calculus geometrically as well as numerically or algebraically. We need both, so in this chapter we'll turn to Cartesian coordinates to see what these formulas might mean in terms of shapes. The first goal, then, is to connect the numbers to shapes. Recall to do this, Dessertes and his fellow Frenchman Fermat imagined a two-dimensional plane and assigned a two-number address to each and every point in the form of x, y. I've only shown one point here, but this assignment of a numerical address is done for all the points in the plane. We can now refer to each point by its numerical address, rather than ambiguously gesturing and saying, that point over there. And now that each point has been assigned its unique address, no two points have the same address, we can now use numbers through algebra to talk about the points on the plane. In other words, and here's the really important thing too. So the graph here, it shows the reference on what they're talking about. It has the x and y axis and the different points of the numerical addresses. On to page 3. Remember, the realm of geometry and arithmetic are connected. Each point is connected to two numbers. We've already seen something very similar to this when looking at the one-dimensional number line. The additional dimensions make the number line idea much more powerful. Often the group of points we talk about forms a shape, like a line or a parabola. These two shapes will occupy a lot of our time. For example, the formula yx equals 2x plus 1 refers to an infinite number of points. In this case, all the points on a particular line. So we have a graph here, or a example figure 16.1b. It's showing the infinite numbers on the point and the particular line, showing the formula pointing at the line is equaling the infinite number of points. So for every x value that we plug into this function, there is a unique y value, which geometrically speaking means that for every point on the line, there is a unique two-digit xy address. That's a lot of information packed into one little formula. And the power of analytic geometry goes even further. Whereas the function y equals 2x plus 1 refers to an infinite number of points on a given line, the function yx equals mx plus b refers to an infinite number of lines, and each having its own infinite set of points. This is because y equals mx plus b is a general formula for a line, for any line whatsoever, and so for all of them. But formulas like y equals 2x plus 1 and y equals mx plus b represents lines only if we're interpreting them as lines. The formulas themselves are only about numbers. They only represent lines when we associate them with Cartesian coordinates. The xy plane. Algebraic formulas of functions are like verbal descriptions of the functions, and the graphs are like pictures of a function. Page 4. Algebraic formulas. Okay. Next it shows an image of inside the box, and it says two sentences. Sentence 1 says a graph is a picture of a function, and a formula is a sentence about a function. So it's kind of identifying what each meant. And then often it's extremely helpful to see the function's behavior rather than merely reading about it. After all, a picture is worth 1,000 words. So formulas and graphs are two different ways to represent functions to stand for the relationship between numbers. And both are important if we wish to understand the relationship, which is what calculus is largely about. 16.2 Slopes. We need to remember another important concept, the slope of a line. A line's slope is just a way of expressing how steep the line is. The slope is defined by the line's rise, how much it changes the y direction between any 2 points on the line, divided by its run, how much it changes in the x direction between those same 2 points. We usually simply say that a slope is rise over run. Here's an example. It shows an image of the x and y coordinates and a slope of a line, pointing out the delta of the x and y, the formula for slope, which is rise over run, and giving an example of the rise versus the run. The rise is going from 1 to 3, and the rise is going from 3 to 7, and the run is going from 1 to 3. And the line formula is still the y equals 2x plus 1, and that is figure 16.2a. Notice that for this function, the slope is 2, technically 2 over 1, which is the same as the coefficient on the other first term, and y equals 2x plus 1. Remember to message in chat, bro. And of course, this is just what we know from the y equals mx plus b formula. The m is the slope of the line, and the b is the y-intercept where the line crosses or intercepts the y-axis. Notice also that we can use the delta notion to define the slope. Slope equals m, which equals rise over run. Rise over run equals delta y over delta x, which equals y to the power of 2 minus y to the power of 1 over x to the power of 2 minus x to the power of 1. Or the coefficients. Remember that when the line slopes upwards to the right, as you move from left to right along the line, the slope is positive. When it slopes downwards towards the right, it's negative. This is just by convention. You might also think of it as reading from left to right. When you go up, the slope is positive. When you go down, it's negative. And when the line is horizontal, there's no slope at all, and is therefore 0. When there's no rise, the numerator of delta y over delta x is 0. Buddy, nerd. I am on. I still need. I'm about halfway. So that's about another 15 minutes, okay? Oh, it's faster than you think. Faster than you think, bro. You gotta go, you said? Okay. Just chill. Take some lessons, bro. You'll be doing this soon enough. I don't even know what they teach in Canada, if it's the same or different. Okay, let me just finish this. On the other hand, a vertical line is officially said to have an undefined slope, since the slope formula denominator is 0, but sometimes people say that the slope is infinite. But even though the slope is undefined, the steepness of the line isn't mysterious. It's just an ordinary vertical line, which is no weirder than any other line. Unfortunately, though, the run part of a rise of a run is 0 in such case, and that's illegal. So in figure 16.2b, it is an image of a figure kind of explaining the negative and positive slopes. The negative going down from left to right, 0 being a horizontal slope, and positive going up from left to right. An undefined slope is completely vertical, undefined or infinite slope. You already know this, even if you had since forgotten it. Why are you talking about it in calculus course? Because a derivative of a function is the slope of that function. 16.3, start with delta x and delta y. Just to be safe, let's remind ourselves of the definition of derivative. Y to the power 1 equals dy over dx equals lim, which is delta x, which equals to 0, is delta y over delta x. All right, buddy. Yeah. We're having a study session. Joe the bot has showed up. I'm almost done. 10 more minutes and then we could play, or I'll stream it. Just log in, bro. I need the views, bro. I need 4,000 watch hours, which is insane. So I need, what was it, Matic? I need 800 hours per person or something. Or that's with 5 viewers. Now I have 7. Yo, what are you typing in chat? What the fuck? Yo, keep quiet, little buddy. All right, let's. From what we covered in the previous section, you should see delta y over delta x and think slope. We've already seen delta y and delta x on the graph of the straight line. Yx equals 2x plus 1. Notice that the slope is the same all along the line. The slope doesn't change, but calculus is mathematics of change, and we'll want to talk about changing slopes. What does that mean? When a curved slope changes, its steepness changes. We'll need something more complicated to better see how derivatives and slopes are connected. So let's look at the function of a simple parabola, the function of the second order power function, yx equals x to the power of 2, which is figure 16.3. We'll get back to that 16.3. The main thing that makes the function trickier than a simple straight line and a trickier in this right way is that the slope of the function isn't consistent. Rather, it's always changing. The slope of a straight line, on the other hand, is the same everywhere along the line. It never gets one more less steep. But let me point out something very important. although we use the specific function yx equals x to the power of 2, what we've done applies to functions in general. That is, it will apply to all manner of functions, not just yx to the power of x2, but as we have drawn something, so we drew a function that we're familiar with. To better see the trickiness of yx equals x to the power of 2, look at delta y and delta x on the graph between 2 points. So figure 16.3a, it shows the parabola opening upwards, which indicates that it's positive, and it is showing that the yx equals x to the power of 2 on the parabola, and we know that the parabola changes throughout the course. Buddy, watch the YouTube short all the way through. I need you to help the algorithm. If you watch the video all the way through, and don't bro. If you dislike it, bro, it's gonna not go viral. I'm posting those types of videos every day on this account. So I already got 60 subs, bro. Chill out. I need to lock in and make some money on YouTube. I already told you I need 4,000 watch hours to get monetized, and then every 1,000 views is like 20 cents. So if I get 1 million views, it's $200 a video. And like it too, bro. And comment, Matic, if you can comment on it too, like just say something cringe, like be like, "Yo, my dog deserve rights." Yo, actually, chill. Watch it for the whole thing, bro. It's gonna get shadow banned. Yo, I'm about to DDoS your internet. Your router's about to get fried. Okay, ready? Back to the study sesh. We are just 4 pages away. 5 pages. Five pages. Figure 16.3b, it is a different figure, but it's the same name. The figure shows the same parabola open up, and it is showing an example secant line with the x and b plots on interfering with the parabola, the positive parabola, and it is explaining how the delta y and the delta x of the rise and run, and how you can use a I can't pronounce it, a triangle to determine the range of it, and it is explaining how the delta y over the x is the slope of it. So the slope of delta y and the delta x is not the slope of the parabola itself, but rather the slope of a straight line connecting the 2 points of the parabola. Point A and point B. This straight line is called a secant because it cuts the curve. Secant comes from the Latin word for cut, which is secere. Think of a section of dissect, but the slope of the secant line isn't what we're looking for. We're looking for the slope of the parabola. The secant line, however, will help. Of course, it doesn't really make sense to say the slope of the parabola, since the slope changes at every point along the curve. In fact, this was a major mathematical problem in the 1600s. Ren de Cerqueres said of this problem, and I dare to say that this is not only the most useful and general problem in geometry that I know, but even that I ever desired to know. And before you say that Descartes needed to get out more, you should know that his life was actually full of adventure and intrigue. In any event, our next step will be to look at the slopes of the curve. 16.4, a changing slope. Look at the next figure, 16.4. We'll get back to that. The strange line that touches the parabola only at point A, and at no other place along the parabola. We call this line the tangent line because the line touches rather than cutting the curve at only one point. Tangent is from the Latin word tangere, which means touch. Think also tangible. Figure 16.4a, it is further explaining the original parabola from, I believe, 16.3a, or B, and it is magnifying the. It is zooming in on the point where the line is not overlapping, but just right next to it, touching only at the single point. Now here's the key. The steepness of the slope of this tangent line at point A shows the steepness or slope of the parabola at point A. So at each point along its curve, the parabola will have a different slope. Look at the difference between the slope of parabola A and the slope of parabola point B. At figure 16.4b now, there is a secant line between A and B. The line is going through the right quadrant, the right upper quadrant of the graph, and the parabola is opening up, so it's positive. And the tangent line is barely not touching it, or 1 point's touching it, and the secant line goes between the parabola. The slope of the parabola at point B is larger, it's steeper, than the slope of the point A, and both slopes are different from the top of the secant line connecting the 2 points. You can now see why we have to speak of the slopes plural of a curve. There are typically more than one, and most curves have an infinite number of slopes, one for each of their infinite number of points. A straight line also has a slope at each point, but each of those slopes is the same at all points. There will be no secant line for a straight line, no line cutting the line for just 2 points. Nor will there be a tangent line, no line that will touch only a single point in the function. For all these reasons, we can speak of the slope of a straight line. 16.5, the derivatives as slope. Earlier said that the derivatives of a function is slope of that function, but there seemed to be a problem with how I phrase this. How can the derivatives be the slope of the function if there is typically more than one? We can easily take care of this problem by qualifying it, saying instead that the derivatives of a function is the slope of that function at that point. The derivatives of a function is the slope of that function at a point. It says that in bold. Remember the earlier definition of derivatives? Y to the power 1 equals dy over dx equals which is delta x, which is equal 0. Which is equal to delta y over delta x. We're going to see how y to the power 1x is the slope of y to x. At each point, that is, y to the power 1x is a function that, when you plug in the value of x, gives you the slope of yx at x. We already know that in general, delta y over delta x is the slope of the secant line between 2 points. Except in the case when a function is a straight line, where delta x and delta y is just the slope of a line, period. But we also know that from previous chapters that, in bold, the average rate of change in y with respect to x is delta y over delta x. Consider the graph of yx equals x to the power of 2 and the slope of the secant line between point A and B. This is figure 16.5a. It looks like it is the same parabola opening up positively. It is now having the deltas of y and x and is explaining the derivatives delta and the secant lines delta. Of course, we're not ultimately interested in the delta y over delta x, but rather of the limit of delta y over delta x as delta x approaches 0. Think for a moment that would happen as we take the limit of delta y over delta x. Suppose we anchor point A and move point B along the curve towards point A, shrinking both delta x and delta y. Let's zoom in a bit on the 2 points as B moves. Figure 16.5b. It is zoomed in on the right segment of the parabola, and it is explaining how point A is anchored, and they are moving point B along the parabola. positively. And now the tangent line seems to have changed. Or the tangent line hasn't changed, but the parabola makes it look like it changed. So the parabola changed. And it is the tangent line is still at point A, but it's not touching point B now. And delta x and delta y approach 0. Notice that at point B moves forward, A, delta y, and delta x both get smaller and smaller. As delta x approaches 0, so does delta y. And this has always been part of what's going on, and we take the limit of delta y over delta x as delta x approaches 0. We haven't just visualized it before now. There's more to it though. Don't forget that these are the slopes of the different secant lines that cut the parabola at points A and B. As point B moves along the parabola towards point A, notice what happens to the secant line as point B approaches point A. The slope of the secant line between point A begins to look and morph like the slope of the tangent line at point A. You might say that the slope of the secant line approaches that of the target line. We could have gone the other way, moving point A towards point B. In that case, the secant line would be approaching the tangent line at point B. There's a lot of movement going on here. Point B is approaching point A. The secant line is approaching the tangent line, and delta y and delta x are both approaching 0. We should expect all this approaching because we're taking a limit, which is built upon a notion of approaching. So all this movement is going on a while. Delta x approaches 0, while delta x moves. Again, motion, change. This idea is that delta x approaches 0. The slope of the secant line approaches the slope of the tangent line at point A, which is just one point of the many ways to explain what we've already learned in symbols. So now it shows a figure of the explaining how the dy over the dx is the slope of the tangent line, and the delta y over the delta x is the slope of the secant line, and the y to the power of 1 equals dy over dx, which is equal to the lim of delta x 0, which is equal to delta y over delta x. So then the derivatives of yx, that is dy over dx, is the slope of the line tangent, is the yx at a point. We'll talk about which point in the following chapter. Also, the limit of delta y and delta x as delta x approaches 0 is in geometrical terms the limit of the slope of the secant line as it approaches the slope of the tangent line. That is, it says this in bold, the derivatives of yx is the limit of the slope of the secant line as it approaches the slope of the tangent line. 16.6. Up next, graphing the method of increments. In the upcoming chapters, we'll do exercise problems with the method of increment and the power rule. But this chapter is exercise free. I want to introduce the basic concepts before moving on to calculations. In the next chapter, we'll look more at how to interpret derivatives geometrically by extending what we have so far in the method of increments. This will help us better see just what we've been doing this whole time. Alrighty, that is chapter 16. We can go over the study questions later, but thank you for watching. Yo, I'm still on the live, but I ended the what's it called? How many chick chat? What do you mean? It said click the link. I don't see a link. I don't see it. Probably doesn't let you send links. Yo, You're right. Ready. I'm looking at it. Oh, I wish. Wait, let me look up a video on how to keep my YouTube up, but also stream Twitch at the same time. Yo, so did you learn anything? So what'd you learn? I'm just kidding. Have you seen that video? It's like, have you seen that video? It's like this. Ready? It's like, what's the difference between an avatar and a bear? They both have big noses. And like the other guy laughs, right? So like pretend like you're laughing. Okay, do you get the joke? Explain it. they're like, yeah. And then the guy's like, explain it. It's like so stupid. That's the whole point. It's supposed to make no sense, and then anyways, let's see here. How to stream Twitch and YouTube at the same time. And I'm a sneaky link. Top tells me. You're reading the stream. W's. Bro, anyway, I'm doing a. Yeah, I'm trying to figure out how to do that real quick. I'm gonna try to keep my YouTube open. I guess I'm gonna have to end the stream first. Anyway, I'm gonna have to end the YouTube and then I'll put it back up. Right. I'm gonna have to end the YouTube, but then I'll put it back up. Buddy.